Hi Ani.
Hi Janakiraman.
Okay, so welcome back. Let me update you on what we did last time. Bobby and I did a very interesting experiment, and we decided to look at the effect of frequency in a general circuit. Okay.
Okay.
So we basically said you take a circuit which is like this, R and C. We are going to apply an input voltage, and we will look at this voltage across the capacitor.
Okay.
Very specifically, we said V in of t is this unit step function, right? So, in fact, on the oscilloscope and the signal generator, we gave a square wave of various frequencies, and then we observed what happens to this Vc of t, and then we also theoretically described, what would happen, right?
Right.
So, just to, remind our students of what we saw last time, if you plot this input voltage as a function of time, it would be like this, okay?
So the voltage, input voltage goes from 0 to 1.
Yes.
At exactly t equal to 0.
At t equal to 0. It's an abrupt step.
Abrupt step.
Right?
So slope is infinity.
Yeah.
For t less than 0, it is 0.
And then
for t greater than 0, it is 1 volt.
Exactly, right?
Great.
So this doesn't exist in reality, but for our theoretical understanding, it is still good enough. And then if you look at this output, I think I used blue last time, so I will stick to the same color coding, Vc of t. And if you look at that, it was something like this. Okay, it was an asymptotic charge up, okay, and Vc of t was 1 minus e power minus t by Rc.
Okay, I was just about to say it looks like an exponential.
Exactly, right? So this is exactly what it was, and as t tends to infinity, Vc of t gets to the final voltage of 1 volt, but for any other finite value of time, it is not at that, ultimate voltage. And of course, if this were to be V naught instead of 1 volt, right, then the expression would just change to something like this.
Makes sense.
Okay, and I would also add the unit step here because it's only for t greater than 0 that
it is valid.
Exactly, right?
Right.
And so, in general, we saw that since it takes infinite time to reach the final value, there's no point in looking at, any RC circuit would take infinite time. So that doesn't give us much information on how fast it is. So therefore, we decided to look at, if you had a faster RC circuit, it would look like this. If you had a slower one, it would take longer, and therefore we decided to simply look at the 50% time. Okay, this was V naught by 2, and if what we found was the t 50% was 0.693 Rc. Okay, and therefore with respect to this number R into C, we were able to talk about slow frequencies and fast frequencies, right? So the RC of course has a dimension of time, 1 by RC therefore is frequency, right, or angular frequency, right, and therefore we were able to talk about high frequency and low frequency with respect to this number, and in fact we chose R last time as approximately as 1 kilohertz. Okay, and C approximately.
You mean 1 kilo ohm?
1 kilo ohm, I'm sorry. 1 kilo ohm and 100 nanofarads. Okay, which implies RC is about 100
microseconds.
Yes. Right? And therefore, all our experiments lined up very nicely with this. If you try to apply a square wave which was much faster than 100 microseconds, the capacitor didn't have enough time to charge to 100, the final voltage. It would just go up, it would come down. You make it really fast, it would almost be a straight line.
I see,
right?
I see. Okay.
All this we sort of observed.
Okay.
Right?
I'm assuming it's a straight line because it is almost tangential to the beginning of the exponential.
Exactly.
If you observe a time, it looks
small
almost
time
linear.
window there. It's the Taylor series of this e power minus t by Rc. You will get, exactly a straight line there, right? So now I thought we should, go one notch up and analyze the same circuit, but for a very different input. Okay, so what I want to do in this lecture and as usual we will discuss the details. Okay, is we have an input V in, okay, the same capacitor, same value also by the way, capacitor C R, okay, and we are going to plot the Vc of t, we are going to observe Vc of t. This time the input is going to be some A sin omega naught t.
Makes sense, because you talked about a step which is the transient response. You talked about the final value being the DC value.
Yes.
Next is makes sense that you would go to a sinusoid.
A sinusoid, right?
Yes.
Exactly. And the reason we want to do this is, you know, we were trying to analyze in the amplifier what happens if omega naught changes. We gave 10 millivolts sin omega naught t. What happens when the omega naught changes, right?
Yes.
So therefore, we have to look at the sinusoidal input and observe what happens to the capacitor, right?
Okay.
So based on our discussion last time, right? Can you make a guess of, you know, what would happen if I applied this? Let's say, obviously I have to tell you now for what frequencies.
Yes.
So let's go low frequency to high frequency with respect to this RC number.
Sure.
Let me also remind the viewers that RC is about 100 microseconds.
100 microseconds.
Okay, and 1 by RC therefore is approximately what? Is what? 10 kilohertz?
Yes, 10 kilohertz.
10 kilohertz, there's a factor of 2 pi, but approximately, order of magnitude is about 10 kilohertz,
Yes.
right? So now, what will happen if I apply a sinusoidal of 100 hertz?
Of 100 hertz.
Yes.
So, if I understand this correctly, so the value of R times C tells you how well, it tells you the time constant of the circuit, it tells you how fast the circuit responds.
Yeah.
So, if I had to take a guess, I would say when you give it a slowly varying input, which is what 100 hertz is,
Yes.
compared to RC,
Yeah.
I would expect that the capacitor will have enough time to charge and discharge.
Yeah.
Most likely I would expect to see the same sinusoid at the output,
Same
because
sinusoid.
I am imagining, you know, at every instant of time the input is changing, the output has enough time to quickly change to the next value every time the input changes.
Exactly. So I would also like to tie this back to a certain observation we made last time. Okay, if you look at when we applied a 100 hertz square wave, okay, if this was 100 hertz, then the output actually would charge up because the RC is so quick. It's almost like
Yes,
this.
that's right.
Right, and it would be it's almost indistinguishable from the ideal square wave
Yes.
because the time constant is so small.
So small.
Exactly, right. Now what we are doing is we are trying to apply an input. I'll show that in red. Okay, something like this, maybe a different amplitude, it doesn't matter. And okay, but this signal is again very slow.
So now can I imagine that sinusoid to be made up of infinitesimally small steps or something like that?
Exactly, right. So you break this up, the sinusoid can be viewed like this. Okay, it's like infinitesimal small steps, right, and each step is like our 100 hertz step that we gave last time. So therefore the capacitor has enough charge to reach each step output, and therefore as you said, the output should technically follow the input
Fairly closely.
fairly closely.
Okay.
Okay. Now, what do you think will happen as I increase it to maybe frequency we always look at, you know, 10 times, because there's no point in looking at 1 hertz, 2 hertz and all
Yes.
that. So let's say 1 kilohertz, 1 kilohertz now.
Okay. So I'm going to take the same analogy as the square wave.
Yeah.
You said that when you did this lecture with Bobby and did the experiment, you said that it was not able to reach the full height.
Yes.
It actually reduced the smaller height and then had to start
Exactly,
discharging.
exactly.
So my guess is something similar might happen. The amplitude of the sinusoid might actually come down. This is my guess.
Okay, yeah. I think that makes a lot of sense because the capacitor doesn't have enough time to charge, and
Yes.
therefore it's trying to get up, but then the input has come down.
Input has come down.
So that will automatically
Yes.
follow. Yeah, good. I think that's sort of very much in line with what we saw last time. So let's go ahead and make the experimental observations first as always, and then we will come back and as usual derive in theory and make sure that both of them line up well with each other.
Great.
Okay. So as usual, you know, there is a breadboard. Okay, there is the resistor R, which is
I assume you had said that it's about 1 kilo ohm.
Yes,
Is that right?
right, exactly,
Okay.
right. That is about 1 kilo ohm.
Okay.
And the capacitor, the guy standing tall here, is about 100 nanofarads.
100 nanofarads.
Right.
Okay.
And these wires obviously are the kit that provide the input sinusoidal wave, and we are also probing the output, right. So as usual here, this VC goes to the oscilloscope, one of the channels.
Okay.
Okay, and this input comes from the signal generator.
I see.
But we are also, you know, looking at this guy on the oscilloscope because we want to compare the amplitudes, right? So we are also giving this to the oscilloscope on an other channel. I think this is channel 1 and this is channel 2 or something. We'll look at that and
We'll
come
look at
back
that.
here.
Yeah.
Okay. So this is the experiment. So for this experiment, just like the square wave, the A doesn't matter. We are fixing the amplitude. We
Yes.
are only going to change the thing. Okay. So this is, let's say, 1 volt. We are fixing it to 1 volt.
Okay.
Okay. The frequency we are going to vary now. Okay. Like I said, from 100 hertz, we'll
Okay.
go all the way to like
Maybe
10
100 kilohertz or something.
yeah,
like
100
that.
kilohertz,
Okay.
not in a linear manner, in of course in a exponential manner,
yeah.
right? So this one we will vary. Now, what do you think are the parameters that we should note down when we?
So I think we'll of course need the frequency.
Yeah,
Maybe
of
the
course.
time period.
Okay, so let me say the input frequeny, F in.
Yes.
Okay, I called it F naught, right?
Yes.
Yeah. Okay, this is in hertz.
Yes.
And therefore we'll also keep note of the time period because
Yes.
RC we know in microseconds, right?
That's right.
So we'll also keep this in seconds.
Okay.
And what
So
else?
input amplitude we are keeping constant.
Yes.
So we don't need to note that down.
Exactly,
But output amplitude might change.
exactly. So therefore we need to look at max of Vc of t,
Yes.
right? The maximum value that Vc of t
Vc
can
of t.
go to.
Correct.
Okay.
Correct.
And the negative value min should be just the negative of that. So I think that should be okay, but we'll not worry about that for now.
Okay. So
Anything
one more
else?
thing, maybe I know that the sinusoid has some zero crossings.
Yeah.
Maybe the zero crossings might move as well.
Okay. So you're saying that the capacitor can take its time to charge and discharge,
Exactly.
and therefore that can also. So can we look at the delay? We'll call
Yes.
that delay for now.
Yes, we
right?
can call it delay for now. Yes.
Delay between Vc of t, okay, and
V in of
V in of t. We'll just make this observation, and later we'll see if we have to give it a different name.
Yeah.
Okay. And so this one will start with 100 hertz. Okay. So I'm going to open this, and this is my sine wave. I'm saying 100 hertz.
Okay.
The period is 10 milliseconds. Amplitude is 1 volt.
This is the signal generator output.
Signal generator. Okay, this is the signal generator. The going here, and what we have now is I need to scale this a little bit, right?
Maybe we need a few, maybe 5 milliseconds per division, something like that.
Yeah.
This is good.
So
Okay.
this seems pretty good. Okay.
Yes.
So let me look at, one by one. Okay. What is this now? This is, I believe this is the input,
Yes,
right? This
yes.
is the input that we have applied,
That's right.
which is between 1 volt and minus 1 volt.
Correct.
Okay. And then I enable the output. I can switch off the input.
Yes.
And you see that both of them are almost in phase.
That's right.
Right,
So
the-
they have the same amplitude. They also seem to be right on top of each other.
Yeah, and they're therefore following each other exactly.
Yes.
Right. So therefore, this is what? This is 10 milliseconds.
Yes.
Right.
Yes.
Max of Vc of t, as you can see, we just look at the orange guy here. It seems to be 1 volt. Okay, this is in volts. Okay,
Yes.
and the delay between the input and the
Yes.
output seems to
Yes.
be 0.
Seems to be 0. We'll say very close to 0.
We'll say close to 0.
Yes.
Okay. So now I will maybe make it 5 times 500 hertz.
Sure.
Okay. The period is 2 milliseconds. Okay. Amplitude is still 1 volt, and I'm here, and maybe I'll make this what?
5.
Yeah. Okay.
Maybe even a little bit lower, I
Lower,
guess.
so that we can see the difference.
Yeah, yes.
This is nice.
Perfect.
Okay. The blue again is the input. I
Yes.
can turn it off. This is 1 volt max peak value, and it
Yes.
has a time period of what? 2 milliseconds.
Yes.
Is that right? Yes. So this is 500 hertz, 2 milliseconds,
Yes.
and
So
now we look at the output.
I can already see that the output peak value is not at 1 volt.
Is not
slightly
at 1
smaller.
volt, right? So if I turn off the input, you focus only on the orange guy here,
Maybe 0.9, maybe?
maybe 0.9 volt, okay? 0.9 volt.
Yes.
The delay between the two, you can, is also, is
I
sort
can
of,
see the zero crossing is maybe, it's a little bit,
yeah,
it's small.
in fact, if I make this further smaller, you can see it more
can see how-
evidently,
that's right.
So I
So
will
that's-
say slightly greater than 0 for now.
Yes.
Okay.
Yeah.
Right. And now I'll go here, and maybe we will look at 1 kilohertz now. Okay, which corresponds to 1 millisecond. So this is 1 kilohertz, 1 millisecond. And I want to come here.
Okay. I can see the capacitor voltage is pulling away in terms of amplitude and in terms of delay.
Exactly.
You can see the two curves separating.
Separating out.
Yes.
And now where is the maximum value of the VC?
Maybe 0.8?
0.7 actually, maybe 0.75.
Maybe 0.75 or something.
Maybe
correct.
0.75. Okay.
Yes.
Here again 0.75.
Yes.
And it has moved further away. Is
Yes.
all I can say. Okay.
Yes.
Sort of. I'll have to use. I'm not the delay. We are not trying to measure accurately. So I'm going to use some strange symbols
Yes.
moving away further from 0. Okay. That's what that double arrow, right arrow means. Now, shall we go straight to 10 kilohertz?
Yes. Sure.
Okay, 1 volt, and this is 100. Now this 10 kilohertz is interesting because the RC itself was how much?
Was,
1K,
was about
1K into 100 nanofarads.
yes, about 100 microsecond. Is that right?
Exactly, 100 microsecond,
Yes.
and this was approximately 10 kilohertz. This
That's
was,
right.
This was
well,
10 kilohertz.
it was I think more like 10 radians per second. I
10
think,
radians per
technically,
second.
right?
Yes, exactly. So I would say, yeah, you're right. I should call it radians per second.
Yes.
Okay, because this is angular frequency, not the frequency. And so 10 kilohertz corresponds to 100 microseconds.
Yes.
Okay, now let's go and see what happens to the output. Wow.
Okay. Yeah. We need to reduce the.
Yeah, exactly.
Oh.
This is nice.
Okay.
The input is much larger now.
Yes.
The output is significantly diminished. And what is the maximum value? Maybe 0.4 volt,
Maybe 0.4 volts.
right?
Yes.
So 0.4 volt,
Yes.
right?
And I'm also noticing something interesting.
Yeah.
The delay has increased so much
Yeah.
that the maximum of one seems to be almost,
Almost.
occurring at the zero crossing of the input. The
Exactly.
maximum of the output.
Right, exactly,
Right?
right?
It suddenly changed a lot.
So when this guy is rising, that guy is falling. So it seems
Yes.
to be okay. So that's great. So is delay the best way to measure this?
So, because see, your maybe not, because you need to find something that is independent of the time period, independent of the frequency.
Yes, right.
Right. So phase.
Phase, exactly.
Right, phase shift.
So instead of delay, I will call this phase.
Yes.
Okay. So 0, it was some angle. Okay.
Yes.
Some number.
Yes.
Around here, we seem to be
Close to pi by 2.
nearly pi by 2.
Yes.
Okay.
In fact, I suspect in the previous case,
Yeah.
it must have been, if you had seen the delay or in phase,
Yeah.
it might have actually been somewhere maybe close to pi by 4 or
Pi
something.
by 4.
I'm guessing.
Okay.
I'm
I'll
guessing.
put a number here.
We'll go back and check it.
Yeah,
We should
okay.
go back because it looked to be significant enough
why
to
don't we do
check.
that, right? 1 kilohertz, right?
Yes.
Input. Okay.
This is good because and yes, I do see that it is not pi by 2,
Yes.
right? Because it is coming a little bit before the zero crossing.
Yes.
So maybe 50-55 degrees, something like that maybe.
Yeah, something.
Right?
Okay.
Yeah.
So we'll just keep this
We'll
at
keep it as approximately pi
pi
by
by 4, right? Pi by 4 is what? 45 degrees.
45 degrees.
Yeah, that's fine.
Close
So
enough.
let's just keep it, okay? And finally, let's go all the way to 100 kilohertz, right? Or maybe 50 kilohertz, right?
Okay.
Wow, this is very interesting. Of course, we need to make this.
Okay.
Okay, now and I also probably need to stop this.
Yes.
Okay, yeah.
Yes.
So the input is swinging plus minus 1 volt all the way.
That's right.
The output is
Amplitude is almost zero.
It's stuck at 0
Yes.
almost, right? Maybe
That's
what? 0.1 volt or something, 100 millivolt or something
Yes,
like that, right?
correct.
So this is 50 kilohertz and this corresponds to 20 microseconds, right? 20
Yes.
microseconds,
Maybe 0.1.
0.1.
Yes.
And
See, now
yeah.
interestingly, I
Yeah.
noticed that it is not even now. The peak of the output seems to be
Yes.
occurring close to the zero crossing. So
Correct.
that's almost pi by 2.
Almost pi by 2. So if you look at this, you're right. So while the amplitude seems to be steadily falling off,
Yes.
the phase seems to have some interesting behavior.
Yes. So it was close to 0 for some time, then it changed a lot, then it's become close to pi by 2 and it's not changing
and
much.
the interesting part is between 100 and 1000 itself,
Yes.
the phase would have changed significantly. Right?
That's right.
Maybe we can look at that. Okay,
Yes.
we will go back, look at. Maybe I look at 200 hertz.
Sure. Yeah. That will give us one more data point.
Okay, and I have to run this, and I have to make this.
Maybe 5 millisecond per division, 10.
Yeah. Yeah.
Yes.
Maybe
Perfect.
right.
Yes. Maybe we should reduce it further so we can see even more. Maybe 1
Yes.
millisecond per division.
Or 500.
Okay. You can see on the X side.
Yeah.
Maybe it's each is about 0.05. So difference is about 0.1 milliseconds.
Correct. Exactly. It's about 0.1 milliseconds.
Yes.
Right. So, and now when I go to 500 hertz.
Okay. So now the difference is close to maybe 0.2 milliseconds.
0.2 milliseconds, right?
Yes.
And then if I go to, of course, 1 kilohertz is okay. So what we are seeing is, it seems to be responding in the 100 to 1 kilohertz range.
That's right.
Very visibly.
Visibly.
But after that, it seems to be hitting.
That's right.
Pi by
I think probably we'll see the same thing when if we go slowly from 1K to 10K,
Okay.
we'll see it responding from pi by 4 to pi by 2.
Yeah.
And then after that, it seems to be not responding at all.
Not responding at all, right?
That's right.
Okay. So this is thing. So maybe I'll just put these two observations down. Okay. One output, right, which is Vc of t, amplitude is steadily decreasing.
Yes.
Okay. 2. Phase moves quickly.
Somewhere close to the center, around that 1
Yeah.
over the RC,
RC, right?
right? Or 1 over 2 pi RC point.
1 by 2 pi RC, where one moves quickly
Yes.
in some region. We'll see what region this is, right? And saturates
Yes.
at pi by 2. It doesn't seem to be going any further. Okay. So now the idea is we have to explain all of this with
That's right.
theory.
Yes.
Right?